Okay, we'll start recording now. Okay. Good afternoon, everybody. Good morning in the other side of the Atlantic. Welcome again for this Instituto de Astrofísica de Andalucía colloquium. And today we will have the talk by Dr. Holly Gilbert from the High Altitude Observatory in United States. And she will talk about space weather in an era of innovative science. So Dr. Gilbert will be introduced by Dr. Anchon Alberdi. Please, Anchon.
Yep. Good afternoon to everybody and good morning to you, Holly. It is a pleasure to welcome Dr. Holly Gilbert to our IAA Severo Ochoa seminar program. Dr. Gilbert is the director of the High Altitude Observatory, which is part of the National Center for Atmospheric Research. Holly has over 20 years of experience in the field of heliophysics, conducting solar research, leading large group of scientists, and participating in outreach and educational activities. Prior to being director of the High Altitude Observatory, Holly was the director of the Heliophysics Science Division at NASA's Goddard Space Flight Center during the years 2017 to 2020. And she was also deputy director of the HSD, the Heliophysics Science Division, from 2015 to 2017. She was chief of the Solar Physics Laboratory from 2011 to 2015. Prior to joining NASA in 2008 as the HSD Associate Director for Science, she was a research scientist at Rice University and an associate scientist at NCAR's High Altitude Observatory. Holly did her undergraduate work in physics at the University of Colorado and obtained her PhD in theoretical astrophysics from the University of Oslo. She has served as the elected chair of the American Astronomical Society's Solar Physics Division and the NASA ESA Solar Orbiter project scientist. She was awarded with the Women in Space Aerospace Awareness Award in 2016 and the AGU Athelstan Spielhaus Award in 2015. Today, she will talk to us about the space weather in an era of innovative science. Holly, welcome to our seminar program, and the floor is yours.
Thank you so much for that introduction. I'm going to share my screen, and hopefully that is all working well. Well, thank you so much for inviting me to talk about space weather. I'm going to focus a lot on solar physics specifically, but space weather falls under a larger umbrella of the science of heliophysics. And what is heliophysics? Well, it really is trying to understand how the sun interacts with the Earth and the other planets throughout the solar system. It's a term that came to be, I think maybe in the early 2000s, but it really is about the system science of the coupled sun-Earth system. And space weather impacts us here at Earth. Space weather also impacts other planets, but of course there are societal impacts here at Earth. Heliophysics begins at the sun, so I'm going to be focusing mostly on the sun. But again, it's really important because of the system science aspect of heliophysics and space weather to understand all of its components, including the coupled system here at the Earth. It's a very complicated, complex science, and so I hope I can at least pique your interest. Let's go back in history, though, before I go into some of the newer observations. This is a large solar prominence taken from the High Altitude Observatory, actually, in 1946. And this is taken through a filter centered on H alpha, and this is a massive structure of plasma contained in coiled magnetic fields. And if you can see the helical structure of this, what we call like a massive flux rope, and the plasma is coupled to the magnetic field lines, and this is erupting away from the sun. You can see, you can see that this extends way above the solar limb. In fact, it's about, I think, 200,000 kilometers above the surface. So this is a really, really large eruption of a lot of mass and magnetic field lines. Now, one thing that I'm going to really hit on during this presentation is the importance of magnetism. And magnetism is absolutely central to our understanding of fundamental physical processes in solar physics, and it spans both time and space. Moving forward in time, 1970s, Skylab was the first space station, but in my opinion, the greatest scientific contribution was its actual continuous monitoring of solar activity. And so the astronaut crews, they would each take images and data that actually really revealed the sun in a way that we've never seen before. Skylab discovered these coronal mass ejections. And in this white light coronagraph, you can see this large white bubble of material. That is a coronal mass ejection. And we didn't know that these existed really before this. Although eclipse observations throughout history, there are drawings, hundreds of years ago even, that show some of these similar bubbles. And so I think people in history had seen these during total solar eclipses, but of course didn't know what they were. And it was through the advent of space-based missions, or these coronagraphs, that we're able to block the very bright disk of the sun and discover these mass ejections in the tenuous corona, the outer layer of the solar atmosphere. It's interesting. Well, actually, this other image at the bottom is also another image showing this erupting piece of material, and that's part of a coronal mass ejection as well. And so, it was a little surprising that these things existed. But what's interesting is that the very phenomenon that Skylab discovered actually caused its demise. There was an unexpected rise in the number of these coronal mass ejections and other radiation that was slamming into the Earth and heating the atmosphere so much that it expanded. And I'll be talking about this. This is one of the impacts of space weather. It impacts our atmosphere and causes an oscillation. It increased the drag on Skylab. And so it began to pull it out of orbit faster than NASA had anticipated. So it actually ended up causing it to fall to the Earth faster than it was supposed to. Of course, our observations have become much, much better, both in temporal and spatial resolution. And this is very important. Of course, now that let me try to restart this movie. There we go. I knew there were going to be technical difficulties at some point. So this is really important. As you can see, these beautiful dynamic eruptions, lots of activity. Having better resolution in both time and space is important for studying the dynamic aspects of the sun. Again, these are space-based observations taken from the Solar Dynamics Observatory. And this is really when the term heliophysics was born. Now, it's necessary to use multiple wavelengths. Here we're looking in the ultraviolet and extreme ultraviolet to observe the corona, the very hot corona. These are different temperatures. This is, I think, on the order of maybe 100,000 Kelvin. The other ones, the yellow one that's about to come on, is about 1.5 million Kelvin. You need all of these wavelengths to really look at the different layers and the different temperatures. And there's an entire slew of dynamic activity, as you can see, very small scale. This is a flare, flaring loops that are occurring. You've seen lots of these eruptions. That's a flare with an erupting prominence. There's also a solar wind. This is coronal rain. There's a solar wind, though, that is constantly blowing away from the sun. It's consistently blowing out its outer atmosphere in a solar wind. All of these things contribute to the field of space weather. So back in 1859, there was a massive solar flare observed by the eye of Richard Carrington, and he made this first drawing of a solar flare. Now, what we're seeing here in the animations, this is of course from more current data, but it's showing that there's a flare, and the impact on the Earth is the beautiful aurora. And in fact, in 1859, they saw aurora down at very low latitudes, which is unusual. Usually the impact of these solar storms and the solar wind create aurora at the polar regions of the Earth, and that's because of the shape of the Earth's magnetic field. But this one was so large that they were seeing aurora around the world globally. And it impacted the technology of the day. The telegraphs were sparking and catching fire. And it was at that point they realized there's this connection. There's a real connection with what's going on with the sun and how the earth is responding. And so again, this was sort of the early stages of space weather. It wasn't called space weather at the time, but it's important because our technology is susceptible. And now the societal impact is even larger because of our technology these days. In 1989, there was a large event. It wasn't as big as the Carrington event. The Carrington event was the largest in recorded history. And this one did strike the Earth, and it caused a widespread power outage. And that's because the Earth's magnetic field, the magnetosphere, has a much stronger magnetic field. And when these storms impact that magnetic field, it induces much larger voltages in systems that have long electrical conductors, such as power lines that run over long distances. And these significantly higher voltages can really damage power transformers. And these transformers are very expensive to replace, and they are not just on the shelf. It's not easy to recover from these types of storms. So again, that's why we need to be able to understand, ultimately predict, and forecast space weather events so we can help mitigate some of these impacts. In 2012, there was an extremely intense solar storm. In fact, the biggest one since the Carrington event. This one did not hit the Earth, luckily. What you're seeing here is a spacecraft called Stereo, and it was orbiting not near the Earth-Sun line, so it captured this huge storm. And what you're seeing, that snow, that's the charged particles, the cosmic rays hitting the detector and impacting the detector. This storm, had it hit the Earth, could have been incredibly damaging globally, especially to the electrical infrastructure. And so we were very lucky to dodge this. If you look at a model of this event, now we're looking down a top-down view at the ecliptic, or the plane of the Earth's orbit. And on the side, there's a slice perpendicular to the orbit, and that passes through the Earth. And I apologize, I know these are very small, probably on your screens. But of course, here the sun is in the center. There are multiple coronal mass ejections. In green is the Parker spiral, and that's the magnetic field spinning around from the solar rotation. That's generated from the sun's current sheet. The red represents particles that are at high temperatures, and they show that the coronal mass ejection, especially the large one that I'm going to point out, is much hotter than the usual solar wind flow. The large changes in density are represented in blue. So if you put these three colors together, it tells us something about the characteristics of the event. So what I want you to notice, excuse me, is that there's multiple of these seams. That's the one, that largest one, that is the one caught by the Stereo spacecraft up here that I just showed. And one of the conditions which contributed to the high speed of this event. Now, the speed of these coronal mass ejections also contributes to the impact of space weather. It's the fact that there were multiple smaller coronal mass ejections launched ahead of it. These events cleared out much of the solar wind material, leaving very little for the outflow of the large event. So it went very fast. It wasn't really bumping into a lot of solar wind. Now, as I said, these colors can really be combined to tell us something about the coronal mass ejection itself. As you can see, you can tell if it's a very hot shock or very dense or both. So these models are extremely useful. And here's a larger view. It's Jupiter. This is the Jupiter up here. And again, I realize you're probably on a smaller screen, can't really see this very well, but I just wanted to emphasize the fact that these coronal mass ejections travel throughout the heliosphere. They have a very, very large reach. Here's a model of that event as if it had hit the Earth. So this is the Earth's magnetic field and atmosphere. And what we're looking at is the magnetic fields represented by those lines and density. So before it hits, you can see the radiation belts around the Earth. This is a lot of energy getting transferred, and it's stripping away basically that magnetosphere. You can see how distorted it becomes. This really creates a vulnerability This is a huge difference between that and how the protective shell normally is. So the macro scale structure and the dynamics of the Earth's magnetosphere are very strongly influenced by these types of storms, but also the solar wind. And this directly impacts the ionosphere thermosphere system here at Earth. Now, I've showed observations and models. I want to emphasize the importance of integrating both. This is very important for forecasting and prediction. So the observations, not just the remote, but including the in situ, inform the models, and the models are getting more sophisticated because we have better observations and it feeds into each other. We still have a lot of challenges though. So I've already emphasized one key challenge in heliophysics, and that is the fact that it's a system science, and that makes it a little bit complicated. Another related key challenge is the vast range of scales that heliophysics covers. Our science goes from the kinetic to the magnetohydrodynamic, which is the study of magnetic properties and behavior of electrically conducting fluids, which is a one fluid theory. So you can study the very small kinetic scales. And this is all depending on what processes we are interested in. And these processes occur on a range of scales from solar wind interacting with comets to interstellar medium interacting with the heliosphere. So it really isn't just central on the sun, which is kind of what I'm showing today. But it really requires an understanding of system dynamics and energy transport across all scales. It's nice, the sun offers a dynamic laboratory for us to study a variety of these processes basically in our backyard. The Earth's upper atmosphere and magnetosphere also are a great laboratory to study these types of physical processes that are shared, like magnetic reconnection, which is also an astrophysical fundamental process. Now, space weather impacts also cover a range of temporal scales, and I want to credit Antti Polkinen of NASA for this slide. Now, this is a little bit of an eye chart, but if you look at the sun, this is really demonstrating the impact of different types of consequences of space weather. So if you have something happening at the sun, the vertical scale is time. So you have minutes, and these concentric circles represent those different time scales. And so first, say we have a flare and an associated coronal mass ejection. They often happen together. If you have a flare within 8 minutes, at 8 minutes, you're going to have the impact of that here at Earth because the in the increased X-rays and radiation are going to hit. And when that happens, it's going to impact potentially like GPS, for instance, and also high frequency communication. So that is a very fast reaction. The flare that reaction in the impact will last for a while, but not incredibly long. But then you have minutes later, energetic charged particles that are generated by the flare. And when those hit, they also impact satellites. And so those interact with the electrical components on satellites. And so that impact is very long. It can last for a very long time. It also impacts high frequency communication and also aviation. And so these different colors, you may not be able to read them, but the orange is aviation. And that really is especially true for the planes that are flying over the polar regions, again, because that's where a lot of the energy is transported, is those polar regions. Now, not only do you have the flare coming very fast, you have the energetic particles coming very fast as well. The coronal mass ejection can take hours to a couple days to arrive, depending on how fast it is. So once the coronal mass ejection hits the Earth's magnetic field, that's when the Earth's magnetic field then can oscillate. And so then you have what we call the geomagnetic storm, and then the power grids can be impacted, and you can see that can last for a long time, as well as GPS, satellites, power and high frequency communications. And also the satellites can be continually impacted because once the Earth's magnetic field starts oscillating, then it can have multiple impacts, substorms. So again, I call this the 1, 2, 3 punch because you've got the flare, the particles, and the coronal mass ejection. And so it's not that this happens every time there is a storm that faces the Earth, but it can happen. So to face the system science challenges of heliophysics, we have, at least NASA has, and the rest of the world also has a lot of missions, but these are the NASA missions, what we call the Heliophysics System Observatory, and these work together. And there are a lot of them, and this is even a little out of date. But there's both remote sensing and in situ, and we really have a three-dimensional context this way, or at least that's the goal. And so just I wanted to make the point that it requires a lot of observations, different types at the Earth, towards the sun. And in fact, I want to discuss a couple of recent solar missions that nicely sort of illustrate the synergy between observations. So this is Parker Solar Probe. This is an animation created by NASA. This is a mission to touch the sun. And I'm sure you probably all heard about it. I know many of you have, if not all of you. This was launched in 2018 and is going as close to the sun as anything ever has. The closest approach will happen in 2025. And it will go within about a little over 6 million kilometers from the surface of the sun. That's super close. Very, very close. And it's the fastest spacecraft in history. So on its final orbits, the spacecraft will reach speeds up to close to 700,000 kilometers per hour. Now, why do we have to go this close to the sun? Well, in order to actually understand the atmosphere and especially the corona, the lower, sort of not the lowest part of the corona, but just to sample that part of the atmosphere provides us with a lot more information about where activity is occurring. So it's really that corona, especially in the lower parts of the corona where the action takes place. Magnetic fields interact, there's a lot of activity. So it's important, it's incredibly important to actually sample that part of the sun. It just hit its mission midpoint with its 12th encounter. And so it's a very exciting mission that's already been really producing wonderful science. Now, of course, there's extremely hot conditions close to the sun. The heat shield, I think, can reach like 1300 Celsius. You have to forgive me my units. I'm used to Fahrenheit. And the instruments behind it, though, in the shadow of that amazing heat shield will remain at about 30 Celsius, something like that. So they are very well protected. The heat shield itself is a couple of panels of carbon composite, and they sandwich a lightweight, like 4.5-inch thick carbon foam core. So this is a pretty impressive technology. And I think it's also sprayed with a specially formulated white coating to reflect as much of the sun away from the spacecraft as possible. Now, that's not the only innovation. There's an amazing thermal protection system. And I mean, that was the heat shield. I'm sorry, the actively cooled system with water that's been really amazing in itself. And also some of the instrumentation is exposed. It's just really cool. The engineering aspect of this is very cool, and it's been working beautifully. Another mission that is dear to my heart, as was said at the introduction, for a while I was the deputy project scientist, and then for a short while, the project scientist on the NASA side for Solar Orbiter. So Solar Orbiter is a NASA-ESA collaboration. And Daniel Mueller is the project scientist on the ESA side. And this is a mission that launched in 2020, February, just before COVID really hit and shut everything down. It was kind of a miracle that it launched with international partners watching the launch, and right before COVID. It's great that it didn't get delayed however long. Anyway, it also has a heat shield that's important because Solar Orbiter is going very close to the sun, not as close as Parker Solar Probe, but within the orbit of Mercury. And the heat shield is sun pointing. It also protects the instruments behind it, but there are apertures for the remote sensing instruments because Solar Orbiter has a combination of remote sensing and in situ instrumentation. That is very important, and I'll talk a little bit about why. The heat shield for Solar Orbiter is carbon fiber composite with multiple layers of titanium, and it's this solar black coating, which is also the crushed burnt bone is the same kind that's used in Stone Age artists. So it's pretty neat. It's pretty neat that, again, a technology that came to be to make this happen. Let me move on just to show you the scale. So again, it's a very truly international collaboration. There are 10 instruments, and so you can see the lead countries for each instrument. There's a PI instrument PI for each instrument, and so the coordination was truly impressive with all of these instruments. Again, having the remote sensing and the in situ together is really powerful. It's allowing the spacecraft to take samples at certain points in its orbit, and also look at the sun to see the source region of the solar wind particles that it's actually measuring. That is really neat. We do this at 1 AU at Earth, but by the time the plasma and the solar wind gets to the Earth, it's gone through a lot of other stuff. So essentially between Parker Solar Probe and Solar Orbiter, we're able to really sample sort of the early solar wind before it gets transformed between the long journey between the sun and the Earth. Here's the 10-year orbits of Solar Orbiter. The other unique thing, besides the fact that it has these remote sensing and in situ instruments, is the orbit itself. And so you can see what's happening is it's using gravity assists by Venus and Earth to kick it out of the ecliptic. And so for the very first time, we're going to image, we haven't quite yet, but we're going to be imaging the polar regions of the sun. This is really important because the magnetic field, the global magnetic field of the sun has a lot to do with those polar regions. And the fact that we've never been able to observe them because we're on the ecliptic, it limits our modeling. We really need that information, not just magnetic field at the poles, but also the flows. And we need that information to really well inform the models so that we can get better. And again, that will help space weather forecasting and prediction. So a very exciting mission. The two work very well together. There's a great synergy. This is recent data from Solar Orbiter. And again, the instrument PIs and the project scientists behind this, they've done so much to really make all this happen. So there was a flare in March of this year, and you can see on the left that it was captured in very high resolution. I don't know if you saw the animation here on let me see if I can do that again. This is a zoomed in region. You can see the Earth is the black circle. You can see a lot of really small dynamic activity, brightening, very, very small. This is what's really cool. This is, we've never observed the sun this close. Solar Orbiter has already made some close passes. It hasn't made its closest pass, but it's really neat to be able to see the sun so up close. Okay, so now that we've seen some of the newest space-based capabilities in solar physics, I'd like to discuss what I think is a missing link in observations, and therefore there's a gap in in advancing our ability to forecast space weather. I talked about the corona a lot, and here's an image of the hot corona with the coronal loops, because the plasma is outlining those, and you can tell. So the coronal magnetic field determines really the dynamics and the structure of the corona. Now, it drives the activity that results in space weather, but how do we actually measure the sun's magnetism? This is a very challenging aspect of solar physics. Now, these fields, they leave an imprint on the intensity and the polarization of the light that it emits. So the observations of the polarized light, though, need to be interpreted in terms of magnetic field. And this interpretation relies on complex polarized radiative transfer community models. So it's not an easy thing to do, but it is one way of inferring magnetic field. I also want to point out that in order to study the magnetic origins of this stuff, we really need a two-pronged approach. We need to understand the very small scale magnetic processes driving these phenomena, as is obvious as we see the very small scale stuff. And a lot of these physical processes take place on very, very small scale. So we need to observe at that scale. But on the other hand, we need large scale synoptic observations because we need to understand the system as a whole. And that really enables the forecasting. I'll be discussing a couple of observatories that fill that need, but first I want to consider some of those physical mechanisms that control the polarization of the spectral lines that originate in the solar atmosphere. Okay, so sort of simply put, spectral line arises from the absorption or emission of a photon when an electron jumps from a bound energy level to another. So in the presence of a magnetic field, the energy level splits into multiple sublevels, and they're at slightly different energies. So what was originally one turns into multiple spectral lines that are slightly shifted in wavelength from one another. Now, the amount of splitting between these sublevels is directly proportional to the magnetic field strength. So this gives us a proxy. The larger the field, the larger the splitting. And the transitions result in basically linear and left and right circularly polarized light in the plane perpendicular to the magnetic field or along the magnetic field. So, excuse me, we've magnetic field measurements in the photosphere, which is the lower layer of the atmosphere, and also the chromosphere, the one just above it between the corona and the photosphere, have been based mainly on the Zeeman effect and have been implemented for decades. The Zeeman effect in higher layers of the solar atmosphere, the corona, are limited to regions of relatively strong magnetic fields. So the corona has some active regions where there are strong magnetic fields. There's another effect, I don't have time to go into it, but the Hanley effect is the modification of the linear polarization of a spectral line by a magnetic field. And this provides diagnostics of regions of weak magnetic fields. And that's where there's a lot of sensitivity ranges. But unlike the Zeeman effect, the Hanley effect does not create polarization. It requires its presence through other physical processes, such as radiation scattering. So physical processes relate observations to magnetic fields. We know that. The observational gap translates to a scientific gap because the global measurements are really needed to constrain models. And this is important, again, for space weather. I know I keep saying that, but this is the basis of the talk, right? So coronal magnetic fields are usually approximated through MHD modeling and extrapolation of photospheric measurements, and they have limitations, these approaches. For instance, the extrapolation models are based on the assumption that the magnetic field is force-free, meaning all non-magnetic forces are neglected at the lower boundary of the calculation, which is not the case in the photosphere. So, let's think about what we need to address these issues. We need ground-based observations, which we have some of in the visible and infrared lines. This requires a very large light bucket to capture a lot of photons and a global field of view. We need space-based ultraviolet lines. This is a largely unexplored area, especially in the unsaturated Hanley regime. Again, I didn't go into any detail about that, but this is a new diagnostic of the magnetic field strength, and we need to understand low in the atmosphere. So ideally, well, as low as possible to the surface, but 1.1 solar radii or lower within a Coulter, which is, is kind of challenging. We also, of course, need to depend on modeling frameworks that are co-designed with missions to really effectively realize the potential of the data. So the communities are really collaborating in a great way to help advance this. Now I'm moving down to the ground because Mauna Loa Solar Observatory is managed by HAO. And the instruments on Mauna Loa, which is located on the Big Island of Hawaii. In fact, there's a view from Mauna Loa to Mauna Kea, which is where a lot of the nighttime observatories are located. And these instruments are designed to carry out synoptic large-scale observations of the sun's activity. And that, again, fills part of that need that I was talking about before, the global context. And we've operated coronagraphs on Mauna Loa since the 1950s. And to this day, we take unique observations of solar eruptions as they occur. Now, DKIST is, I think you've had a talk on this last year, and DKIST is amazing. And it's just now been online for a while. And it's the most powerful solar telescope in the world, the largest. Also, it provides extremely high resolution data that is needed. It really acts as that microscope, as the need to get the small scale and to observe very small. So the two in conjunction are great. Mauna Loa, of course, I just wanted to talk a little bit about that. If you notice the the K corona. This is our coronagraph white light data here, and it's an internally occulted refractive coronagraph. The field of view is very low. It goes down to 1.05 solar radii, so 0.05 solar radii from the solar surface. This is allowing us to observe and understand the source regions of the coronal mass ejections. COMP is another instrument, and here you're seeing an eruption from COMP as well. COMP is the coronal multi-channel polarimeter, if I could speak. And this is an instrument to observe the coronal magnetic field with a full field of view in the corona. And it obtains information about plasma density and motion as well. It records intensity and linear and circular polarization of lines iron 13 and a couple other lines as well. And it detects the plane of sky field direction, but also the line of sight field strength. Again, plasma velocity and Doppler velocity. Here you can see that image here. In addition, we also have had observations of the solar chromosphere. Here you can see H alpha. So Mauna Loa has been operating for a while. It has a lot of data available from decades ago, if you're interested. Now, here's an example of the power of the coronal multi-channel polarimeter COMP. This was a university-led effort to map for the first time the global magnetic field of the solar corona. Now, Yang et al. Used COMP linear polarization and Doppler data to derive density from COMP line ratios, and this really that allowed them to determine the coronal magnetic field in the corona. This is 2D, but still exciting advancement. And so K-core, again, moving back to the white light coronagraph, is this purple or this blue region here. That's the Mauna Loa field of view, and that's K-core. This image is like from a community-led paper and shows the very early stages of a coronal mass ejection. Now, let me go a little bit into more detail about why this is important. This is allowing early warning data for solar energetic particle events. So this was a study where they used K-core and also NASA data to analyze an energetic proton event in 2017. So the data, here's the NASA data are surrounding the Mauna Loa data here, and you can see the different perspectives. So stereo is at a different perspective as the other data. And these were coupled with a model to show the region was actually magnetically connected to the Earth. And again, this is one of the things that Solar Orbiter is amazing at doing as well, is making those connections. So the connection allowed transport of energetic protons and caused a storm. What they were able to do is identify the source region in K-core of the gamma rays. And so this little yellow circle that you may or may not be able to see where the arrow is pointing, that is the location of the gamma rays. So again, this is an important element to space weather, making these connections from the source throughout the heliosphere. We've recently upgraded COMP, and there's now a wider range of wavelengths, a larger field of view. And these types of observations are really needed. They're going to help us understand these physical processes that I keep talking about. Here we're looking at inferred values of the coronal parameters of iron 13 on February this year. So the top row from the left shows the intensity here, and also the Stokes Q and U, which provides linear polarization, and then the fraction of the total linear polarization on the right on the top. The bottom row shows the line of sight velocity, the line width here, the direction of the magnetic field with respect to the horizontal, so the azimuth, and the direction on the right, the direction of the magnetic field with respect to local radial direction. So this is exciting. The data is coming online. We're very excited to have this enhanced capability. UCOMP is really a pathfinder to Cosmo. And what is Cosmo? Well, Cosmo is what we hope to be constructing in the next several years. I mean, it's in the early stages, but this is what we've identified as a path forward to transition Mauna Loa into Cosmo. And it has three main components. First, there's the white light coronagraph, the K-core, which we've already had operational and implemented. There's what we call the ChroMag instrument, which is a chromosphere magnetometer. And I'll talk a little bit, I'll just show briefly about that in the next slide since I haven't talked about that yet. But the third component of Cosmo is the large coronagraph. And to show you a scale, there's a person standing here. This is an artist drawing. This is a 1.5 meter diameter telescope, and it has the capacity to gather light to really obtain those measurements of the line of sight component of the magnetic field in the corona. Again, UCOMP is a prototype of the large coronagraph of Cosmo. So the goal of Cosmo is to enable the fundamental research behind understanding predictability of the Sun-Earth system. Right now, we're trying to select a good site for Cosmo, and this requires very, very good coronal dark skies, dark in the daytime. And I can show you here. It's not marked, whoops, but the thumb blocking the sun acting as an occulter at sea level on the left has very bright coronal skies, whereas if you're up 10,000 feet, you can see that on Haleakala that it's a much better coronal viewing. And so this is one of the things that goes into our site selection activity. Just briefly, ChroMag is, again, will make full disk synoptic measurements in multiple layers, including the chromosphere. I don't have time to go into this, so if anyone's interested in learning more about it, let me know, and I certainly can go into some more detail. Okay, so again, I don't know if you can read this, but I wanted to just make the point that, this has been an extremely exciting era for solar observations, and the synergy between these observations is very powerful. So DKIST will help us understand how and why the corona heats up so dramatically, as well as other things. Parker Solar Probe is providing a survey of the outer corona. It's tracing the flow of energy and exploring what accelerates and heats the solar wind. Solar Orbiter is examining how the sun creates the bubble of charged particles, the heliosphere, in addition to other things. But again, the power of working together is advancing our field in ways that's been unprecedented. And part of that is really the modeling aspect. So space weather forecasting and prediction is going to rely basically on basic research enabled by the novel observations and creating sophisticated models. So we need high computing power as well. So it's the observations, the computing power, and the modeling all together. And I haven't talked much about modeling at all, so I wanted to touch on that as well because it's a very important component of space weather. So HAO has been leading the development of the state-of-the-art MHD model MURAM, and this is for realistically simulating the coupled solar atmosphere from the interior through the atmosphere all the way to the corona. And so the MURAM code can now model the whole course of solar active region evolution. So flux emerges from below, from the interior, and that is shown in the photosphere magnetic evolution at the top left panel. So here's this is magnetic field here. It goes into the solar atmosphere. It produces flares and eruptions in the corona, and this is shown here in the middle and the lower row. This is synthetic EUV emission images. So we're looking down on the top of the active region similar to the top row here, and from the side. So these are simulated in different lines. This is very exciting because the realism of this model, it's achieved through sophisticated treatment of the energy transport and the thermodynamics of different layers. So also the MHD code is able to accommodate the extreme physical conditions and the separation of scales that's represented by the different layers of the atmosphere from the interior to the corona. So this is a great advance in modeling. MURAM has also been part of another large team effort. It was advanced, the code itself was advanced to cope with the challenges of solar flares specifically. So this is a simulation of the entire life cycle of a flare for the first time using the MURAM code. And it was optimized to run on GPUs, and that opened the possibility of it being able to conduct this type of simulation. Also, it was able to allow us to run them in real time, which really is important. If we're going to model solar eruptions and use them for space weather, that's really important, the real-time aspect. So MURAM is now able to bridge the massive variety of scales that I've talked about necessary to simulate an entire life cycle of a solar flare. It's also beautiful to see. We also need the capability to model coronal magnetic field evolution. And so here's a solar eruptive event model, and it represented, the field lines are represented by all these lines interacting. This is an MHC simulation of a coronal mass ejection that was near the solar disk center, and it produced X-ray class flares, which are the very strongest, and also a very fast Earth-directed coronal mass ejection. And this shows the buildup. So you can see the buildup of the pre-eruption coronal magnetic field and the onset of the eruption. There's a lot going on here, but the random shearing of the field line foot points is representing the effects of the turbulent convection on the sun. And it's imposed at the lower boundary to drive the background coronal heating. It's found that the synthetic soft ray emission produced by the simulated pre-eruption coronal magnetic field, and that is shown here at the bottom, it's very qualitatively similar morphology as the observed X-ray image, which is on the right. So the simulated is on the left here, and the actual observations on the right. So the shearing also drives large amplitude alphane waves, and these produce the wiggles and the large kinks in the open field lines. And some of that is what you're seeing as the magnetic field lines interact. So ultimately, the goal of these types of observationally guided simulations is to determine the realistic three-dimensional magnetic structure of these outgoing coronal mass ejections. Okay, so I have to at least mention that, you know, we also need to model the geospace regime. So I've talked so much about the solar aspect, but again, there's an entire field of geospace observations and modeling. And in fact, we're making great strides in trying to really model the entire system, the whole geospace. And there's recently been a NASA Drive Center for Geospace Storms that was selected and funded to do this. And you can see also there's a multi-scale in the geospace environment. And so there's, you know, having to resolve critical mesoscale processes down here. Really, there's cross-field dynamics. It in itself is another field. It's a subfield, but it's related with a lot of different spatial scales and difficulty in its approach to modeling. Exciting stuff. So I just to make a few closing thoughts. You know, we are becoming more inclined to travel in space. You know, we're going to at some point, hopefully within our lifetimes, actually send astronauts to Mars. And so space weather is very important if we're going to do that. Humans in space are more susceptible than we are here on the Earth. We're protected by the magnetosphere and the atmosphere. So, you know, space weather has definitely grown in importance over not just past several years, but over the last few decades. And, you know, there's no reason to expect that this trend won't continue, where it's going to become more and more important as we become more technologically advanced. And in fact, the sun is really picking up in its activity cycle right now. So we're going to be facing a time called solar maximum in the next couple of years. Now, hopefully I've emphasized enough, this really requires fundamental research. And that research is enabled by these innovative observations and also by the sophisticated modeling. So it's a nice circular team effort. And, you know, it also, speaking of team effort, it really requires coordination and collaboration between government, academic, commercial entities, both nationally, internationally. I think, you know, the more people, the more groups, the more brains we have addressing this, the better. And that's really going to help us, you know, to ultimately predict space weather. We're not there right now. And with that, I think I will just say thank you and take questions.
Thank you very much, Holly, for this very nice talk. And as you say, yeah, let's start the round of questions. And Jose Carlos, I think you can manage the question and answer session. So go on.
Okay, thank you very much, Holly, for a beautiful, comprehensive, and very illustrative talk. I should say that I've learned a lot during your talk, and well, I'm sentimentally close to HAO because many of my friends are working over there. But I should say that looking at the long history of contributions to solar physics, not only in mere science but also in instrumentation, it's admirable. So I have already a few questions, but probably it's better for the others to start. And well, maybe I can start. So I've appreciated very much the historical aspects overview you gave, and I wondered whether HAO did contribute already to Skylab or not.
Yes, well, that's a good question. In terms of hardware, I think they did, and I actually began my career at HAO as an intern, and turning the Skylab data, digitizing Skylab data. So this is a long time ago. So I began with the actual data of Skylab, and I do think that HAO contributed to the coronagraph. They have a very long history of building coronagraphs. Yeah. And so, yeah, I should know for sure, but I've been under the impression that yes, that they in fact did the coronagraph for Skylab, and SMM, which was also another old mission, and yeah, it was nice coming on board, looking at Skylab data as sort of the beginning of my career, and then seeing at that time SOHO was coming online, and it was just like, wow, wait, the sun is incredible. So, yeah, they have a very long history of successful coronagraphs.
Yeah. So Luis has a question.
Yes. Well, thank you very much for your presentation. It was really very interesting, very exciting and motivating. I would like to ask you, because you mentioned some of the upcoming instruments for measuring magnetic fields in the chromosphere, the CHROMAG instrument, I think, and also the large coronagraph, but you didn't give me many details about them. Can you please explain a bit the timeline of CHROMAG, for example?
Absolutely. Yeah, CHROMAG is actually being worked on here in Boulder right now, and it was supposed to be deployed to Mauna Loa a year ago, but with COVID delays and everything, it's still not deployed. I think we're hoping by the end of this calendar year that it will be deployed and functioning at Mauna Loa. And so if that's the case, then we have the K-Corona working, the CHROMAG working, and then the large coronagraph the design is being worked on now. Again, it's using UComp as a prototype, but the large coronagraph is being designed with a group in Italy right now. But yes, CHROMAG is almost complete. It's just been getting it past the finish line.
Okay.
And Alfred Devine is the PI. So okay. Yeah, he, if you wanted to reach out, or I can connect you with him if you need.
Okay. Yeah, I can do it. But what type of instrument is it? Is it a spectrograph with a polarimeter, or it's a filtergraph?
I should have left that up for. Hold on, let me, before I say, because I want to make sure I'm actually. It's a spectrograph. It's a spectropolarimeter. Why can't I say that word today?
Well, it's difficult.
I know, but I say it all the time. And so it's so it's an imaging spectropolarimeter, and it's going to be observing in helium, H alpha, calcium, iron, and it's actually flexible, so new wavelengths can be added. And it's
full disk, right?
Full disk, yes.
Okay.
Yeah.
Okay.
Yep.
And how about funding for the large coronagraph?
Great question. So we are in the very first phase of COSMO, which is the site selection process. So we were given some funding from NSF to do the site selection and to design the large coronagraph. So what the next step is, we need to get funding for construction, and that's not guaranteed at the moment. I mean, we're very hopeful, but once we get through this first phase, which will take another probably 2 years or so, we'll be proposing for the actual construction of COSMO. So yeah, even just selecting a site has been challenging. Yeah, we're taking into consideration lots of factors, not just the scientific viability of the coronal skies, but also cultural aspects,
Sure.
geopolitical, and so yeah, it's definitely it's a lot of challenges, but we're hopeful to get a site.
It's a big project and
Yeah.
a big instrument, a very big instrument. If you manage to build it, it will be a breakthrough.
I agree. Yeah, I think it will be such a great addition. You know, again, the synergy between DKIST and COSMO would be really great.
Maybe this is one good reason to select Haleakala as the site for.
I would love to. I would love to.
Synergies.
Yeah, it would be wonderful. There's a lot of politics and cultural issues related with the Hawaiian volcanoes, and so we're very much respectful of especially the cultural aspects. So we're not clear as to whether it's going to be an option, but it's something that we're hopeful.
Okay, thank you.
Yeah, thank you.
But I've heard you have recently delivered or formally delivered a VISP for this.
Yes.
So, do you have any breaking news about the instrument and the behavior?
It's working. It's producing scientific data, and I'm proud to say it was the first operating instrument. It was the first one that was finished with with all of the calibration and everything. So it's definitely been working. I've been not bothering Roberto and Alfred. I've been asking them to, at some point soon, we need to do some science, and so. Maybe I don't know if they have anything yet. They've been very busy, both of them. But yeah, hopefully soon they'll be. I know the science data is coming down. But to actually to do some science with it is exciting.
It would be nice for us to listen to your results from the instrument, because it is a really challenging instrument.
Yes, indeed. I'll let you know if Roberto, if we do a seminar or something related to this, I'll definitely keep you posted.
Yes, please. So, in about space missions, are you planning new space missions, or can you tell us a bit or about your current plans?
Sure. So HAO has historically, I mean, not actually, that's not true, because we've done coronagraphs in space, but we've been ground-based for many decades in terms of our focus. And so we are now currently trying to explore space-based instrumentation and missions. And so we are looking to, the NASA potential opportunities coming up, and are working in collaboration. But that's, we're very hopeful for the future to collaborate with others as well, in terms of looking at opportunities. And so sort of the capabilities that I was talking about in terms of getting magnetic measurements of the corona would be great, or the chromosphere from space is ideally, and I know that there's efforts going on in other places as well. So I am hopeful. I hope that the communities know how important these measurements are, and I hope the support comes enough to where something gets funded to go to space in these regimes, for especially, the coronal magnetic fields is great, but also, even there's still unexplored chromospheric regimes as well. So we're definitely interested in looking and working towards doing something in space. And hopefully maybe collaborations with you in the future as well.
Okay. Well, if there are no more questions,
I have a question, Jose Carlos.
You have one? Okay. I didn't see your hand.
It's on the logo. It's curiously there. Holly, I have a question from a person that is out of the field, but on the field of planetary science. You mentioned in one of the last slides the importance of space weathering to the travel to Mars, but I think you need to mention the travel to the moon or the
absolutely yes
basis on the moon.
It's absolutely as important in that's likely to occur. Well, it will occur sooner than going to Mars.
Exactly.
So absolutely, yes. So absolutely, the moon, the mission, the human missions to the moon are also susceptible to all this. So it's again important to.
Another point related with the moon is I studied the mineralogy of asteroids and the moon, and one of the products that you can find on the moon is helium-3, which is produced by the solar wind.
Yeah.
So if you study space weathering, maybe you can have a good relation to where to find helium-3 on the moon and how to extract, or the production is too slow. I'm talking about million years.
Yeah. I don't know the details, but I know that there have been previous proposals to look at that and actually do space weather type research from the moon. You can use the moon to do various things, but specifically I don't know. But I think there are interesting potential opportunities there to utilize.
Maybe we can close the cycle, because if you use the sun to find helium-3 on the moon, you can extract that helium and give to Jose Carlos to launch Sunrise 7.
That's it.
Right.
That
was the beginning
of bringing in from the States. We can bring it from the moon.
From the moon, yeah.
It's probably is difficult.
To study the sun again and to search.
Maybe in such a trip there will be no delays. No trading conflicts, no.
No shipping problem. It's just direct from the moon.
Okay.
Okay. Thank you.
So thank you very much, Holly. It's been again a wonderful talk, and we hope to see you once again here in Granada. You visited us for this orbital meeting.
Yes.
So let's do it again.
That sounds wonderful. Yep, look forward to it. Thank you so much for
and say hello to all the colleagues and friends over there.
Will do. Thank you. All right. Enjoy the rest of your week. Bye.